Hello and welcome to this Unisensor microsensor lecture. My name is Lars Hauer Larsen and I am CSO here at Unisense and responsible for production and development of Unisense microsensors. In this presentation I will give you an introduction to how our pH electrodes are designed and working, which hopefully will familiarize you with them and help you applying them correctly. In this lecture I will cover the following topics. First, I will explain how they are made and how they work. I will then turn to the specifications of the electrode and give some comments to them. Then I will explain two of our customizations, the needle electrodes and sharp tip electrodes, how they are produced. And at last, there will be a short troubleshooting section. Unisense pH electrodes are made for research and experimental applications where a small electrode is needed. The electrodes work in principle like the well-known glass pH electrode, which is one of the oldest and most used sensors in the world. Our electrodes are just smaller and can therefore be used for non-destructive measurements in natural samples or applied where volume and space is limited. The electrode tips are produced in our microsensor lab, where we are experienced in shaping glass tubes to microtip designs. Two capillaries, one of lead glass and one of a pH-sensitive glass piece, are shaped so they fit perfectly into each other. The tip size of the finished pH electrode is determined by the diameter of the capillaries. The pH glass is from below pushed into the hanging lead glass capillary. With use of a heat coil and looking through a dissection microscope, the glass capillaries are melted together. With help from a gravity-induced pull and the heat coil, the pH glass is shaped and hereafter cut to the desired length. The heat coil is used to melt close the pH glass capillary, and the lead/pH glass capillary is now ready for electrolyte filling. All glass pH electrodes, including Unisense micro pH electrodes, respond to the proton activity and actually not to the concentration. There is a close relation between concentration and activity, but factors like temperature and salinity influence the activity of the ions. It is beyond the scope of this presentation to go into detail with this. Please consult scientific reviews for more information. These schematic drawings illustrate how the electrode works. This section of the glass membrane illustrates that it consists of three layers: an inner dry glass membrane and an inner and an outer glass hydrated layer. The hydrated layers are very thin, in the low nanometer range. Protons diffuse in and out of the hydrated layers. The concentration of protons is stable in the inner layer because the electrolyte is buffered. The concentration of protons in the outer layer is in equilibrium with the concentration of protons in the sample. In alkaline solutions, the outer layer will lose positive charges and subsequently the potential of the outer hydrated layer will be negative. In contrast, the outer hydrated layer in an acid solution will gain positive charges and the potential of it will be positive. If the concentration of protons is different in the two hydrated layers, an electric potential gradient will establish across the glass membrane, which is only dependent on the activity of protons in the sample, which again is a function of the sample pH. This pH-dependent electrical potential is measured by including the pH glass membrane in an electrochemical cell, where the outer hydrated glass membrane potential is the only potential in the cell, which is dependent on pH. The cell consists beside of the glass membrane of a silver chloride electrode placed in the pH electrode electrolyte, a reference electrode, a salt bridge, which makes connection between the reference and the pH electrode. The connection between the reference electrode and the salt bridge/sample solution is ensured by a liquid junction. The sample solution or the calibration buffer acts like the salt bridge. The cell voltage is measured by a millivolt meter. The glass membrane of the pH electrode has a very high impedance, and due to this, and the small area of the pH electrode tip, the impedance of a pH electrode is in the gigaohm range. To keep the measured potential stable, the input impedance of the millivolt meter must be significantly higher. We recommend at least 10 to the 13th ohm. Only pH meters of the highest quality live up to that. We can therefore not tell whether our electrodes can be used with a third-party pH meter. We only guarantee the pH electrode specs with use of a Unisense meter. The voltage of the cell ideally follows this equation. As seen, E is a linear function of pH as if E0 is constant and the temperature stable. E0 is the sum of the potentials of the silver chloride electrode in the pH electrode, the inner surface of the glass membrane, the external reference electrode, and the liquid junction. These potentials are stable and not affected by the sample pH. The second part of the equation is the potential of the outer hydrated layer, and assuming stable temperature, the potential is only dependent on the sample pH. At 25 degrees Celsius, the ideal potential change per pH unit change is 59.2 millivolt, which is called a Nernstian response. In reality, the change is typically a little less than this. In contrast to amperemetric sensors, we cannot strengthen the tip by increasing the tip glass walls. The resistance of the glass membrane will be too high if we did so. Therefore, Unisense pH microelectrodes are more fragile than amperemetric microsensors with comparable tip sizes. We therefore typically recommend using larger tip size for pH electrode compared to other Unisense sensors for profiling in matrices with hard particles like sediments. It must, however, be balanced against the need for spatial resolution. Consult the web guide about tip size selection or get our input on the choice of tip size before ordering. I will now turn to the actual performance of the pH electrode and give some comments to it. Recall that these specs are only guaranteed with use of a Unisense pH meter. The limit of detection is stated to be 0.01 pH units, which equals 0.59 millivolts. However, the detection limit will be affected by the application in question. The detection limit could be better or worse than the specified, depending on the actual application. The measurements can easily be affected by electrostatic charges and electrical noise. The response time is also affected by the high impedance. The higher the electrode impedance is, the slower the electrode will respond. The response time is longer if electrodes are moved between samples compared to response to a pH change within a sample, because handling typically induces electrical interference, which increases the time needed for stability. Needle versions will normally have a slower response due to equilibration time for the liquid sticking to the needle tip when moving the electrode from sample to sample. We use the definition 90% response time, meaning the time for obtaining 90% of the 100% signal. 100% response time is not used because in theory 100% response time is never obtained, as the signal change approaches the 100% response asymptotically. The curve illustrates the signal from a pH electrode when changing the pH in a sample from one pH value to another, and how 90% response time is defined. The linear range is between pH 3 and pH 9. The pH range in which the electrodes exhibit Nernstian response is guaranteed from pH 4 to pH 9.2, but typically it is linear down to below pH 3. They do respond to pH changes at higher alkalinity, but they do not anymore have a strict Nernstian response, thus more calibration points are needed. The model name indicates the tip size of the electrode. Thus, a pH 50 have a tip diameter of 50 micrometer. We produce them with tips diameters from 10 to 500 micrometers, but we can custom make them with any tip diameter between 10 and 750 micrometers. The spatial resolution the electrodes can be applied with is determined by the length of the pH glass. The area-specific resistance of the pH glass membrane is very high, and if it becomes too high, the performance of the electrode is seriously compromised. The thickness of the pH glass membrane determines the surface area specific resistance, and therefore we must balance fragility, surface area, and electrode performance. Smaller electrodes have a small surface area balanced by thin glass membrane. Larger and more robust electrodes have a higher surface-specific resistance, and thus the surface area must be larger. The spatial resolution the electrodes can be applied with can therefore not be higher than the length of the pH glass tip. For the smallest pH 10 and pH 25, this is between 50 and 100 micrometers, and this grows with electrode diameter. See our website for details. It is possible to increase the spatial resolution of the measurements by approaching the layer of interest in an angle. This way, the electrode tip is not so prone to breakage, as the tip is somewhat flexible for lateral tension. For measuring pH on hard surfaces with biological activity in thin layers, this is a good approach. The lifetime and storage conditions. The expected lifetime of the electrodes depend on the tip size. The hydrated layer is gradually degraded but continuously replenished, which causes loss of glass membrane material. Therefore, small electrodes with thin glass membranes have shorter lifetimes than larger electrodes. This process is faster at high temperatures compared to low. Therefore, store your pH microelectrode at room temperature or colder. pH 10 and 25 electrodes typically stop working within 6 months because the glass membrane is very thin, but larger electrodes can work for years provided not broken. The outer hydrated layer should be kept wet, therefore store the electrodes in DI water, and combination electrodes should be stored in 2 molar potassium chloride. Unisense pH electrodes are made for high time and spatial resolution pH measurements, where larger and more robust electrodes cannot be used. Thus, the long-term drift of our electrodes is not as well characterized as larger standard electrodes from suppliers of such electrodes. The drift will typically decrease over time and will typically be within a few millivolt per week. We recommend, however, to calibrate as frequent as convenient for all important studies. The electrodes stand up to 5 times atmospheric pressure without being pressure compensated. However, as other Unisense microsensors and electrodes, we can pressure compensate the inner parts of the electrode so they do withstand full oceanic pressure. When pressure compensated, they are tested to be able to withstand 600 bars. This photo shows a pH electrode mounted in a Unisense in situ amplifier, where an oil-filled membrane transfers the in situ pressure to the electrode electrolyte. For all applications where the electrode is pressurized, it must be used with a Unisense ref in situ, which withstand pressure as well. Temperature interference. The absolute temperature is included in the equation for ideal electrode response to pH. The slope of the calibration curve will therefore be affected by the temperature. At pH 7, where the concentration of protons and OH- ions are equal, there is no temperature influence. But in both alkaline and acid samples, temperature changes will affect response to pH, and potential errors can be made. Within a few degrees Celsius change, and especially at near neutral pH values, the interference is below the detection limit. Only at pH values far from neutral pH and at several degrees Celsius change, the interference is above the detection limit. Not only the pH electrode response, but also the reference electrode and its liquid junction will be affected slightly by the temperature. And because Unisense pH electrodes are used with different reference electrodes, we have not implemented a temperature compensation. Therefore, calibrate and measure at approximately the same temperature. Recall that temperature influences the activity of protons in samples and buffers, and the electrodes will react to this. Consult review articles discussing pH measurements and temperature for more details. I will not in this presentation go into details with all the adaptations and modifications we can do to a pH electrode. This is covered in the quick guide, but I would at this point describe how a needle-embedded electrode is made. We make needle-embedded versions of the pH electrode in order to give some protection to the glass part of the electrode from being damaged. We make them in two different versions, PHN and PHNP. The latter is made for piercing membranes. This is a schematic drawing of the tip of a PHN electrode. The needle protects to some extent the pH glass, but the glass is still fully exposed to the sample solution. The needle and the glass part of the electrode are glued together inside the needle, so no sample liquid will intrude into the needle. This would otherwise cause a huge carryover effect moving from sample to sample. The pH glass functionality is destroyed in contact with glue, and therefore there must be a cavity between the needle and the pH glass. This cavity results in an increased response time because the cavity liquid must get in equilibrium with the sample water before a stable signal is obtained. Therefore, the response time of a PHN electrode is generally long compared to non-protected glass electrode. This cavity significantly limits its applicability for profiling in biologically active matrices like sediments, as material will be pushed into this cavity and will be stuck there. Such material will influence the pH measured in other layers, and the measurements might not reflect the real pH value. The material stuck in the needle tip might be very difficult to rinse away after use. For profiling in sediments and biofilms, we strongly recommend using a non-needle protected pH electrode. The PHN electrode must not be used for penetrating membranes. This will inevitably cause a breakage of the pH glass. The PHNP is made for puncturing membranes. To protect the fragile pH glass, the pH glass is completely embedded within the needle. A window is grinded in the needle metal about 1 millimeter away from the needle tip. Calibration and sample liquid are thus allowed to enter the needle and reach the pH sensitive electrode. Liquid is prevented in intruding the needle further back due to glue between the glass and the metal. Like the PHN, the PHNP electrode must be used with a reference electrode, as we cannot make it in a combination version. Thus, for measuring pH in membrane-closed bottles, the PHNP electrode must be used with the Unisense needle reference electrode, the REF-NP. The electrode must be rinsed and without liquid before puncturing the membrane, so sample water can enter the needle. The electrode couple can only measure the pH of the bottle liquid one time and cannot follow real-time pH changes. The liquid in the needle is only very slowly equilibrating with the sample liquid and can therefore not follow pH changes. After removal of the electrode, the needle tip will be filled with sample water. Before the electrode penetrates the membrane, the needle must be thoroughly rinsed with DI water and dried by blowing air into the needle. Otherwise, it will take really long time for obtaining a stable reading in the next sample. The PHNP cannot be used for profiling in biologically active matrices like sediments. It is made for sample pH measurements in membrane-closed bottles only, and special attention to careful rinsing procedures is necessary. Another useful customization, which I would like to mention here, is the tapering of the tip so it easily penetrates biological membranes like egg membranes or intestine walls. This is done by melt stretching solid glass at the tip. If a membrane-included object is fixated in an agarose gel matrix, there is usually enough liquid connection to the reference electrode placed outside the object. I will now turn to troubleshooting pH electrodes which do not anymore have a normal performance. These photos demonstrate an intact to the left and a broken one to the right where the pH glass membrane is missing. The most frequent reason for pH electrodes failing to calibrate is due to broken pH glass membrane. In most cases, the tip is broken at the point where the pH glass and the lead glass are melted together. Broken pH electrodes are quite easy to troubleshoot. If the pH glass membrane is damaged or broken, the millivolt/pH meter will measure the potential between two silver chloride electrodes. This results naturally in a stable signal, typically between 50 and 100 millivolts. This would also be the case for small electrodes like pH 10 or pH 25, where the glass membrane is simply degraded too much and therefore have received end of life. It is easily tested whether the resistance is low, indicating a broken pH electrode, by lifting the reference electrode out of the solution where the pH electrode is placed and inserting it again. When the reference is out of the solution, the signal will float, but the signal will immediately and within a second return to the signal observed before when the reference is inserted into the water again. Unfortunately, there is no possibility of repairing damage to a pH glass membrane. If the electrode responds slowly to pH changes and does not give an instant response, the problem could be fouling on the pH glass membrane. The electrodes tolerate almost all possible cleaning substances like alcohols, acid, detergents, proteinase solutions, etc. So it is recommended to insert the pH electrode in different cleaning solutions to see if this solves the problem as the first attempt to remove the fouling. If this does not remove the fouling and restore normal performance of the electrode, a physical cleaning is the only solution. For larger tipped electrodes like pH 50 and larger, it is safe to wipe the tip with a piece of soft wetted fabric or paper. If you hold the electrode so the tip points away from you, the wipe direction must always be the direction the tip points, never against the tip, which will impose a risk of tip damage. For pH 25 and pH 10, physical wiping might break the thin glass membrane. For physical cleaning of these fragile electrodes, we recommend that you hook the electrode up in a microprofiling system and gently insert the electrode into a soft matrix, which will give some shear force on the fouling material and remove it. The best we know of to do this is Oasis flour foam. It should be wetted before inserting the electrode. For pH 10, which is extremely fragile, an agar gel could be used in the first place to see if inserting of the microelectrode tip in this soft medium removes the fouling. Thank you for watching this Unisense microsensor lecture. I hope you enjoyed it. If you have any questions, you are more than welcome to contact us at sales@unisense.com.